Okay, thanks a lot for inviting me to give a presentation on MLscript, which is a programming language that we are developing in my research group here at HKUST in Hong Kong. So this talk is focused specifically on the very core part of the MLscript type system, which forms a Boolean algebra of structural types, as the title implies, and how that helps us do principal type inference in this language. Okay, so a bit about myself first. I started as an assistant professor in HKUST in February 2021, and I'm focused on type inference, subtyping, compilers, optimizations, metaprogramming, all this kind of stuff. And of course, I'm always open to collaborations if you want to work on research-related projects on things that JetBrains cares about, such as Kotlin or other things like that. Right, so let's get into it. You already all know JavaScript and TypeScript probably, and so the problem of JavaScript is that while it's widely used, it's also very error prone, as everyone knows. TypeScript gives JavaScript types, and so it improves on it, but there are still limitations, as we will see. And so what I'm saying here is that MLscript is a more principled and more powerful language that could be a nice alternative to TypeScript. So, okay, I'm not gonna dwell on this, but JavaScript is probably the most used language. It runs everywhere on most devices, right? Because it's the language of the web, right? So it's probably the most portable language, even more than C, because basically web browsers are implemented in most devices. And so the problem, as you know, is that in JavaScript, there are no type annotations. And so when you have a function like this and you want to call it, you're not exactly sure what to pass here as the argument, right? And the way to know that would be to read the documentation, but the documentation may not be very specific, or it may get out of sync. The alternative is to just read the code, which is really not great because you don't really want to read other people's code just to know what sort of arguments to pass to a function. And moreover, the code is not always there, right? Sometimes you have interfaces where the code is not present. So that leads to buggy codes that's not very nice to develop and to maintain. So this is where TypeScript comes in. In TypeScript, you have JavaScript, but you add these type annotations with a colon followed by a type, and that tells us the compiler, the TypeScript compiler, what to expect in arguments of what functions and what these functions return, and it allows it to do a lot of stuff, right? It catches a lot of errors at compilation time, but it also allows refactoring and code analysis, and it's also a form of documentation that is checked, and so that it checks, TypeScript checks that it doesn't go out of sync with the code, right? So that's all good. But okay, so the general trend, this is just kind of a marketing slide. The general trend is just that programming languages have become more and more typed if you think about it, right? So Python is not in this graph, but even Python got types, static types recently with type annotations and a type checker. JavaScript got types through TypeScript. Languages like Scala and Kotlin improves the type system of Java. Swift improves the type system of Objective-C, etc., etc., etc. Right? So it's a global trend, and the goal is to continue this trend a bit further for the case of TypeScript. So first of all, let's be clear on what we mean by a static type in this context, right? So the fundamental insight is that types represent sets of values. So for example, you have the type of numbers, which includes all the values that are numbers such as the value 2 or the value 1. I have the same thing for string literals, which form the type of strings. And then you have composed types, such as the type of records with a field x that is of type number, right? So that's a valid type, and it represents the set of all records that happen to have a field x of type number. So x, the record with field x of type 2 is one of these elements, is one element of this type. But you also have records with more fields, right? Because the record that has field x and field y is an element of the type that specifies that the record has a field x, right? But it's also an element of the record type that specifies it has a field y. Okay, so it's an element of both. So this creates an intersection between the two types, and this intersection can be represented by this extended record type. So from this, we can construct a notion of subtyping by just saying that subtyping is the same as set inclusion, right? So T1 is a subtype of T2 if the values of T1 are included in the values of T2. And this gives us a lot of interesting relationship. For example, you have subtyping, you have what we call width subtyping for records, meaning that you can forget some record fields. So X number, Y number is a subtype of just X number. And then you have depth subtyping for records, which means that you can also upcast the type of each field. So X of type number is a subtype of X of type unknown, and itself is a subtype of type unknown. So unknown is the type of everything, right? Unknown is the type for all the values we don't know anything about. So any value is of type unknown. On the other hand, never is the type of no value, right? So it is the empty set. And so never is just the type of every other type. So the goal of the type system is to characterize the shapes of runtime values at compile time. And importantly, it has to approximate these shapes, right? It cannot just run the program to see what's the actual shape of the value, because you cannot always run programs. It may not terminate, or it may take arbitrarily long, etc., etc. So we need approximation, and the default assumption in most type systems is to be conservative. So meaning that when the approximation doesn't tell the compiler whether something is really safe or not, it will by default say, okay, it's not safe, right? I'm not sure this is safe. I cannot prove it is safe. So please change your program, write it in a different way, in a way that's more obvious from the point of view of static types, and so that we can be sure that your program doesn't have an error. So it raises a compile time error if it's not sure. That's the default assumption in most type systems, right? But not in TypeScript, as we shall see. So this leads to the notion of a sound type system. So a sound type system is a type system that doesn't lie. It detects problems, and when it type checks, when the program type checks and the type system is sound, and you haven't used any escape hatches, then it means that you shouldn't get any runtime errors, any runtime type errors, right? And this is known as the mantra, well-typed programs do not go wrong, that many people are probably familiar with. So in JavaScript, you can have type errors. For example, if you're trying to call methods on a string where the string doesn't have these methods, for example, and this should not happen if the program is well typed and there are no escape hatches, so no unsafe casts, essentially, right? And so this leads to the limitations of TypeScript, which is also a very popular language and is growing very fast, actually, almost reaching the most used mainstream programming languages. So in TypeScript, we have a lot of interesting features, such as singleton types and intersection and union types. And these features are quite unique. They are not really in many mainstream programming languages. So literal types are the types of specific values, right? So the literal type 1 is the type of specifically the value 1, which is the type of number. Intersection types are types for the intersection part of two types, right? And union types similarly. Then you have parametric polymorphism, where you give type parameters to a function, and then you can use these type parameters in the type annotations. Okay, nothing surprising here. And more importantly, you have this feature called flow typing, which infers locally refined types based on conditionals. For example, here we have a function that takes a parameter s, which is a record with a tag of value 0, and the field a, which is any number. So it's either this record or another record where the tag is actually 1, and the field is named b in this case, and it's a string, right? And so we cannot really do anything useful out of the box with a parameter like this, because we don't really know. We just know it has a tag, right? We cannot access the two components. But when we switch over the tag and we write the case where the tag is 0, then TypeScript can actually tell us that the A field becomes available, right? Because it can statically rule out this case from the union, knowing that the tag is 0. So this case is impossible, right? And this is type checked, and it's well typed, and it works out. S.tag has the union type 0 or 1, right? So then you can call foo with a given record, and this is a subtype of this part of the union. So it's a subtype of the union, so this works out. So there are problems with TypeScript, as I mentioned.
Wait.
Yeah.
You said something about values as types, but didn't say explicitly the verbs dependently typed language. Is it somehow related?
So, sorry, can you repeat? Your voice is.
You presented some types which are parameterized by values, but it didn't say any words about dependently typed languages. Is it somehow related, or is it complete distinct feature of the language?
Right. So this kind of starts looking like dependent typing, but it's not really dependent typing actually. So you see that these are literal. These are the types that happen to also be values, but really they can be encoded pretty straightforwardly with classes, for example, right? See, if number is a class, you can make a class 1 that represents the value 1. So there's nothing really special about them. It's more of a convenience that even primitive values have their own type, but it's not really, it doesn't give you the power of dependent typing, right? You cannot, for example, in types refer to actual values you don't know the value of, right? So for example, if you have an X in scope, you cannot refer to X in the type B in a meaningful way, right?
Okay.
So,
okay.
Yeah. Okay. So the problem with TypeScript is that there are many soundness holes because the language was not really designed to be conservative by default. So and moreover, you need a lot of type annotations when you go to TypeScript from the JavaScript, which means that there's a big burden to get the advantages of static typing. So especially when you're a JavaScript developer and you have existing code in JavaScript, you may not want to annotate everything manually, and it can be a big effort, right? And so here's an example of TypeScript that basically silently lies, right, as a type system, meaning that it's unsound. If you define a class foo that has a field number of type number and a function test that takes either a foo, an instance of foo, or a record with a field p. Okay, so in the body we just test whether x is an instance of this class foo, and if it is, we access the field a, which we know is in foo. Otherwise, we access field b, which we know is in the other case where x is not a foo. Okay, so this makes sense. However, TypeScript lets us call test both with instances of foo, but also with actual records that are not instances of foo. And this is due to the fact that in TypeScript, class types are equivalent to their bodies, right? So this record type with a field a of type number is equivalent in TypeScript to the type foo. And so this actually returns undefined, which is not a number, even when you have all the feature flags in TypeScript to prevent implicit undefined. And so it's unsound, right? This should not type check in TypeScript, given the way it represents class types, which is not very nice. And so this is part of the design of TypeScript, right? As many people know, they just wanted to throw types onto JavaScript programs and without caring too much if they made always sense, right? And so it has many holes. So here's a funny video that I think is interesting to look at that explains some of the design decisions in TypeScript.
But there's still different types.
Now I gotta see. So is the sound okay? So maybe I can just.
There is an echo somehow.
Sorry?
The sound echoes.
Okay.
These two types identical. Well. Oh, they're objects. Okay, well then we got to go look at the item property. Yes, they let's say it was foo of string and bar of string. Yep, they're both string. We're good there. Okay, now let's look at the next property. Well, in order to do that, we need to make a foo of string. Okay, and a bar of string. Well, they just got one bigger now. Oh, let's look at the item property of that. Yep, that's good. Let's look at the next property of that. Oh, foo.
Sorry?
Probably you need to either mute yourself or the presenting window.
I'll mute myself. Yeah, thanks for the tip.
But there's still different types. And now I got to see, are these two types identical? Well, oh, they're objects. Okay, well then we got to go look at the item property. Yes, they let's say it was foo of string and bar of string. Yep, they're both string. We're good there. Okay, now let's look at the next property. Well, in order to do that, we need to make a foo of string. Okay, and a bar of string. Well, they just got one bigger now. Oh, let's look at the item property of that. Yep, that's good. And let's look at the next property of that. Oh, foo of string. Oh, off we go to the races, right? And it's basically turtles all the way down, right? And and what do you do? What do you do? I mean, in fact, I remember we talked to some of the Microsoft research, like there's a famous person, Luca Cardelli from Italy, who worked on structural typing back in the 70s and the 80s, and is one of sort of the world-renowned experts on type theory. And then so great, he's at Microsoft Research, let's go talk to him. And he goes, oh, no one knows how to solve that problem. What do you mean? Well, and it turns out that all of the type systems that do structural typing, they cheat. And the way you cheat is you go, okay, well, I guess we'll just keep going. But then once we've seen enough of them, we just say, I've seen 5 now, and it seems to just keep on going. We're just going to stop here and say, let's assume it's true. And then let's check all the rest. And if that also turns out to be true, that's good enough. It's true. So we have the turtle cutoff. You know, it's about 5 turtles down. We kind of go, you know, we're going to stop here and call it true. It's funny, we got this.
Right. So as you can see, you can basically summarize this type system design philosophy as you only live once, right? Basically, the compiler does the best effort to try to check the types, and sometimes there are recursive looking things, and it just stops at some point. And instead of saying, you know, I cannot check this type, please help me out, it just says, yeah, it's true, these are subtypes. So this may lead to runtime errors, of course. So here's why the problem is more serious than this video may make it look like. The problem is that type checking, subtyping in a structural type system like this, with parametric polymorphism and with records and unions, so it's actually an undecidable problem, right? So if you look at the way we can, so okay, the way to see that is that you can encode in these types, in these structural types, basically regular grammars, right? So you can do that by using a type that represents sequences using the classical head and tail encoding. So it's either empty or a record with a head and a tail, and that represents a sequence of strings or characters, whatever. And then you can encode things like, for example, the grammar of palindromes, which is given here, right? So this is a non-terminal S, and we're saying that a palindrome may be the empty string, or a palindrome may be the character A, or the character B, or the character A, B, followed by a palindrome, followed by character A, or B, followed by palindrome, followed by B, right? And so the way you represent this is that you make a type called palin of T, where T is the tail, right? T is what comes after the palindrome. So it's parameterized, it's kind of in continuation passing style, right? It represents a palindrome followed by something. And so we can then encode all of these cases one by one. So for empty palindromes, we just have the tail immediately, right? For those that are just A or B, we have A or B and then the tail. And then we have recursive cases, right? So for this case, we start with an A in the head, and then we have a palindrome, which is this S, which is followed by an A again, right? And then the tail, okay? And then we can do the same for the last case, and that encodes the type of palindromes, and it's a subtype of sentence that we saw here, right? So it characterizes basically a regular language, which is the language of palindrome. And moreover, you can generalize this to any sort of grammar, right? If you put the grammar in Chomsky normal form and you encode it using CPS types, then you can encode any regular grammar. And that's a problem because basically what this means is that subtyping decides regular grammar inclusion, and regular grammar inclusion is an undecidable problem. So what this means is that there are no possible correct TypeScript type checker, right? It will either be unsound or it may not terminate on some inputs, right? You cannot implement the TypeScript type system correctly. So that's a problem, right? We want to find a way out of this. And the way to work out of this is to be conservative by default rather than forgetful, right? So let's go now to the problem of type inference. So I'm going to introduce it very quickly. Type inference here, what we mean by type inference and principal type inference is what we call global type inference, meaning that you don't need to specify any type, right? You can just write functions without type specifications, but they are still typed and checked at compile time. So if you make an error somewhere and you pass the wrong argument in the wrong place, you get a compile time error, right? So you can still provide public signatures if you want, but you don't need to, and they can be automatically generated by the compiler. So type inference, global type inference could be thought of as a solved problem. Okay, I have a question. Why iso-recursive types do not work in such cases? So what flavor of okay, yeah, so the thing with iso-recursive types is that it makes the subtyping problem kind of trivial because two recursive types that have the same structure will not necessarily be subtypes of each other, right? So iso-recursive types as opposed to equirecursive types mean that you have explicit constructors and destructors for the recursive types that you need to write in the program to consume or produce these recursive types. And it's kind of similar to encoding recursive types using explicit data types like algebraic data types. And so it's much less powerful, right, and much less flexible. And for providing types to a language like JavaScript, you may want something more flexible, like equirecursive types, right? Right. So going back to type inference, global type inference has existed for a long time in the ML language family, and they can infer all the types in a program without problem, most of the time, right? And the problem is that these type systems are quite inflexible, right? They don't have implicit subtyping, meaning that if you want to leverage subtyping in a language like OCaml, you need to use explicit casts or explicit coercions, right? They are checked, but they need to be written in the program by users, which is actually pretty disruptive because you need to provide the entire type signature every time subtyping is used. So basically, that means that people don't really use that very much. There's no object-oriented programming features, and of course, you don't have literal types, unions, intersections, and all that interesting family of types. So what we want to do is do principal type inference for the kind of types that TypeScript has, meaning equirecursive types, literal types, unions, intersections, etc., etc. Okay, so but what do we mean by a principal type? So the principal type is the best type that can be given to the term or to your program. So if you look at a function such as identity, which takes an x and returns x, you can give this function type number to number, but it's not as general as it could be, right? Because you can also give type string to string, and neither is more general, neither is better, right? So in this case, the principal type is for all a to a. So it's quantified, this parametric polymorphism. This is just a type parameter, right? And this is the most general type. And this means that when you infer most general types, you don't need to go back in your program and add some annotations in some places because the compiler always infers the best type for you. So principal type inference for a language like TypeScript is hard. In fact, if we don't restrict it in some way, it's undecidable because type checking is undecidable. And so what we have to deal with is subtyping and parametric polymorphism. So we want polymorphic type inference, right? If you look at approaches like Flow, the Flow type system for JavaScript, it doesn't do polymorphic type inference. It only infers monomorphic types, which is a problem. For example, it couldn't infer the type of the identity function, right, with the for all. Moreover, we need to solve constraints that involve unions and intersections, and we'll see that this is actually quite involved, okay? Such as when you have a T1 on the left and a union on the right, this is complicated to solve, and we need to correctly handle flow typing, okay? So now that we get all this out of the way, this is finally time to introduce the MLscript language. And if you have any questions so far, let me know. Please interrupt me if something is not clear. And so let's see the goals of MLscript. So the eventual goal of MLscript, which is not completely implemented currently, is to be compatible with TypeScript and JavaScript. So we want to make it interoperable, right? We want to be able to leverage all the existing libraries written in TypeScript or all the existing type bindings, TypeScript bindings for existing JavaScript libraries, right? And so this means we will be able to interoperate with existing TypeScript and JavaScript projects, which should make it very nice to leverage the existing ecosystem and to gradually migrate from existing languages. We also want to have a sound type system. So we still have unsafe casts, like most actual practical programming languages, but we want that if the user has not used any casts, then the program is provably type correct, in the sense that you won't have a runtime type error. And moreover, we want to have this nice notion of principal type inference, which means that all the parameter types and all the return types are inferred, and the type inference engine doesn't guess wrong, right? And as a more anecdotal advantage, we also would like a more concise syntax, which is expression-oriented and that has less boilerplate. So let's look at this last point first. Here's a TypeScript code snippet that you may define to manipulate some classes, C1 and C2. So it does some instance tests on C1 and C2 in order to know which field to access. Nothing surprising here. This uses flow typing, right? Because there's a conditional that tests if the parameter is an instance of C1, which rules out the C2 case, meaning that we can access the A field in C1. And this is the same in MLscript, where you can see that the syntax is expression-oriented. So, for example, you can use case expressions, which is the same as basically instance tests, where we're testing whether the parameter x is of type C1, and if so, it accesses the field A, etc. Okay. So here's a quiz for people who haven't fallen asleep yet. Here's a JavaScript program, which doesn't have any type annotations, right? So it's not a TypeScript program. It takes a S as a parameter and tests whether S is an instance of some existing class 1. If it is, it returns its payload, assuming so that there's a payload in this case. Otherwise, it returns 1, 2, 3, right? And in MLscript, you would write it this way with a case expression. In case of class 1, you return as the payload. Otherwise, you return 1, 2, 3. So can anyone suggest what the type should be in TypeScript or in MLscript? Any ideas? So here I have class 1 of payload or 1, 2, 3. So that would be the parameter type or the return type. I feel like it kind of mixes parameters and returns here, right? So this would be a function from something to something. So the 1, 2, 3 will be included in the result. So yeah, a union with 1, 2, 3 will definitely be there. And the parameter should be an instance of class 1 or something else, right? So it's a bit unclear what type to provide to this definition. So here's a trial. You can say, okay, let's say that the function foo for all A has a parameter s of type either a class 1, where the payload is string, which you can represent as an intersection type, or A, where A can be something else, right? Something else than the class 1. And this returns either the string payload or the value 1, 2, 3. Okay, so that looks good. And TypeScript tells you it's good. TypeScript tells you, yeah, that checks out, right? It uses flow typing to figure out that you can access the payload here. Okay, no problem. Well, actually, it's unsound. This type is not correct.
Yeah, doesn't look good enough because Like string as a payload type is pretty arbitrary to me.
Right. So it's not the principal
Over,
type.
I guess.
Yeah, you're right. It's not the principal type, but it's fine. We would just pick an arbitrary type. Yeah, but actually, this arbitrary type, TypeScript tells us it's good, but it's not good. And here's an example where it's not good. The problem is that you can make up a class that extends class 1, but that has a payload that's of an unrelated type, right? And if you call foo with this, TypeScript will tell you it returns a string or 123, but actually it returns 13337, right? And this is because when you instantiate foo with the type argument unknown, basically this whole union collapses to just unknown, right? Because if A is unknown, then A or something else is just the same as unknown. So basically the type collapses to unknown to string. Actually, it should be string or 123, right? Which is not the correct type. Okay, so it lets you pass anything, and it doesn't actually check that if it's a class 1, then it should have a payload, which should be checked because we are doing an instance of check here. And if the parameter is an instance of class 1, we're accessing the payload. So, yep.
The TypeScript basically messes up the co and contravariance.
Oh, so there's a problem that TypeScript mixes up contravariance and covariance. Yeah. Thankfully, nowadays there's a flag in the TypeScript type checker to make sure this doesn't happen, right? But it doesn't solve this issue, right? This issue is really an issue of flow typing in a sense. TypeScript's implementation of flow typing is not sound. So here's the MLscript.
Could you repeat why incorrect type is incorrect?
Because if you look at the type like this, and you instantiate it with A equals unknown, so any possible value, right? Unknown is like any, the top type. Then this union collapses to unknown because unknown or something else is the same as unknown, right? The union of the set of everything with another set is the set of everything. So basically that makes the parameter unknown. And basically it means it doesn't check anything about the parameter. It doesn't check that if it's a class 1, then it should have a payload with the corresponding type. Does that make sense, or is still not very clear?
So
Yeah,
the problem is in the argument or in the result type?
Specifically unknown.
I think you spoke at the same time. I couldn't catch it. Can you repeat, please?
The problem is in the type of the argument or in the type of the result? Or both?
What about the type of the result?
Well, it looks fine.
This one looks fine. So we can make it crash, right? So we can make it have a runtime type error. Because TypeScript...
Wait, the result type is an error. It is argument of the error incorrect or the result of the error incorrect.
So it's the whole thing that's incorrect, actually. There are several types you could give in TypeScript that would be sound, but this particular combination is not correct, right? So you could have for type, for example, unknown to unknown. That would be fine. But this particular combination of a parameter type and a result type is not right. So you can try it out. If you actually pass something like this, it will return the value 1337. But the type says it returns either a string or the value 123. So this is clearly not right. Yeah, the type is lying here. And why does this happen?
I have a question.
Yeah.
In one exact moment, TypeScript compiler drops the 1 to 3 parts from the result type. I just can't see how it happens.
So this is a typo in my slide. This should be string or 123. I'm sorry about that. Maybe I can correct it to be clear.
So that's the error, not a error from a TypeScript compiler.
So let me just make it clear. This is the actual type should have updated now. Yep. So okay, TypeScript thinks.
Yeah, that was the only part that I was confused about. Thank you for
okay. Yeah. Okay. TypeScript thinks it has this type and it doesn't at runtime. Okay, that's the gist. And this happens because this class is an instance of class 1, okay? So it falls into that branch and it accesses a payload, and the payload may not even be there, right? There might not be a payload defined in class 1, okay? So let's have a look at the valid type, which is also a principal type for this definition. So in MLscript, the type that is inferred is for all A, either a class 1 with a payload of A, so this is kind of similar to the TypeScript one, or something that's not a class 1. And the result is either this A or 1, 2, 3. Okay, so this is a negation type, this tilde. It means any value that's not a class type. So any value that will not fall in the instance test for a class 1, that will not go into a class 1 instance test, right? So what are negation types? You can go back to the set theoretic understanding, where basically, if you have a type T1, then its negation is all the values that are not in T1, okay? And basically, the negation unioned with the type is basically the set of all values. So in particular, we have interesting relationships, such as not unknown is the same as never. So not top is the same as bottom. Unknown is also not never. And string is a subtype of not number because there are no values that are both strings and numbers, basically. And in particular, 2 is a subtype of number, and high is a subtype of string, and negation is contravariant. So basically what we have is the value 2 is a subtype of not the string high, which is interesting, right? And then if you look at what the types we have defined so far, which are basically the TypeScript types, unknown, never, union, and intersection, to which we have added the negation type, then this forms a Boolean algebra, okay? If you take equivalence to be defined as subtyping both ways, S equivalent to T is a shorthand for S is less than T and T is less than S. And thanks to this, we can actually apply a lot of reasoning tools that are natural and pretty intuitive about Boolean algebras, which are the algebras of, which is the algebra of Boolean numbers and things like that, and also power sets, unions, and intersections, and things like that. Yeah. So here's a taste of the formalism. We're not going to go through these rules. I'm just gonna show a few interesting rules out of these ones, which are the rules specifically to make the type relationship a Boolean algebra. So we have reflexivity here. We have something that says that any type T is a subtype of top. A union of T and not T is a supertype of top. If T1 is a subtype of T2, then not T2 is a subtype of not T1. So negation is contravariant. We have the usual and or type subtypings. So when you have this little square here, it means that you can basically take the symbol and put it upside down. So for example, here, T is less than top this rule can also be applied the other way around, where this means that bottom is a subtype of T, right? You can flip both at the same time. Then you have distributivity, transitivity, and the rest are basically specific to MLscript. They describe things you do with unions and intersections of records and function types. And they also have this context. You have a context on the left of subtyping rules, which is used for recursive types, right? So these are more complicated rules that are specifically for the semantics of MLscript. But overall, this forms a Boolean algebra. And moreover, these specific rules, this set of rules, are the rules for are an axiomatization of Boolean algebras, basically, right? So what does it mean more specifically to be a Boolean algebra? Actually, there's quite a lot of conditions you need to satisfy to be a proper Boolean algebra, as defined as a complemented distributive lattice. So there are several ways of defining Boolean algebras, but this is the one of the easiest one. And if we break it down, basically it means you have to support all of these properties, right? You have to have a partially ordered set. That means it's the subtyping is reflexive and transitive and antisymmetric. And moreover, you need to have join and meet operators with the usual properties, commutativity, associativity, etc. You need to have bounds, least upper bound and greatest lower bound. And for any type S, you need to have a negation not S, right? Where the S or not S is top, everything, unknown, and S and not S is bottom, right? So moreover, it needs to be distributive. And once you have all of this, then suddenly all of the rules about Boolean algebras you can apply, and it just works out, right? And here we actually prove some properties, some of these properties, in order to show that MLscript subtyping is actually forming a Boolean algebra. So this is a proof for associativity. You can just use some of the rules that I've shown before, and there's also one for commutativity, etc., etc. So that's nice, but how do we handle object-oriented programming, right? Because basically what we've shown here is the typing rules for very simple types, like function types, records, and actually we need to handle object types and classes, right? And so the way MLscript does that is that it decomposes class types, such as my class of A, where my class is defined like this, into an intersection of several components, right? So there will be one component per record field in the type. So each record field in the class will be intersected, will be an intersected record type with only one field, because these are elementary record types in the syntax of types of MLscript. Moreover, there will be what we call a nominal tag, which represents the nominal identity of this class, right? So our type system is structural, but it has a sprinkle of nominality to make sure that we don't have the unsoundness that we saw before due to the being too nominal, right? So in MLscript, a class type is not equivalent to its body because it includes a nominal tag that says, look, I'm actually a runtime instance of my class. I'm not just any record of these things. And moreover, the second idea is to solve the problem of undecidability, is to make sure that the fields as declared in the class types are regular, right? So that the recursive class types that you declare form regular types, meaning that all the occurrences of the class you're in the process of defining should be applied at the same type argument. So this is not valid, right? And this restriction means that we can no longer define things like the palindrome, the type of palindromes, right? Because if you remember, it applied itself at different arguments inside. But this is too restrictive. You may want to have sometimes return type of this shape, and for this we introduce methods which are distinct from types and don't participate in the structural subtype checking, right? So you can still access them. They still kind of behave like fields, but it won't try to check. It won't try to check recursively that the two methods that a class with methods is a subtype of a class with other methods, basically. Okay, you can still define inheritance hierarchies. You can still do overriding and refining of method types, etc., etc. But you won't have structural checking for methods, basically. Okay, and so let's have a look at how the MLscript type checker actually works. And I feel like
do you have a type for class itself? For example,
I have
when you write a method that applies that accepts current object, so there you will have a variable that represents the type of this class, and when you inherit, it becomes the variable that it represents the type of inherit class, stuff like that. So the question is about type of class being currently defined. I think it is distinct from the name of the class that you are specifying with the declaration.
So you have Yeah. I think you're talking about this class tag, right?
I want to define a field that accepts a type of the class, my class, that is currently being defined.
Mm-hmm. So for example, you want X to be of type my class of A, for example.
Not exactly my class of A, but the class is currently being defined.
Yeah. So it basically makes a recursive type, right? And that's fine.
I guess the question is about self types and typing like this reference or self reference.
Yeah. So
self-types probably better.
We do have this feature actually. I can demo it later. It's kind of a minor feature that's not presented in the core type system of MLscript, but we do have these types. Yeah. I can show you later if you want. Yeah, it's a nice feature that can be used for fluent interfaces, right? I think C# supports it, and Scala, and I guess Kotlin supports it too. Not sure.
And we should probably mention OCaml.
Oh yeah. In OCaml you have something like that too. Yeah. Yeah,
we
want
your words in the slides about Haskell and OCaml doesn't have object-oriented features was misleading. It was 10 slides before.
Sorry, I couldn't get it. What?
A few slides before, you had a slide about no object-oriented features in Haskell and OCaml.
Yeah. Okay. Yeah,
and
sure.
O in OCaml probably means something. So it was misleading.
I know. Yeah. So what I meant actually was that. Okay. Yeah. Yeah. OCaml has an object-oriented system tacked on, right? But yeah, that's true. Okay, this line is not completely accurate. But the thing is that you cannot use it without explicit coercions, right? And that's a big problem for normal object-oriented code, where you want, for example, to pass an instance of a subclass, or you want to make a list of heterogeneous values of different classes. You cannot do that in OCaml without explicitly casting things to the parent type, right? So
yeah, I understand.
I guess
I wrote you about this in the email.
Yeah, you're right. I should have changed this line. It does support object-oriented programming, but I would say a version of object-oriented programming that's quite powerful, but that also has pretty strong restrictions. Yeah. So the goal here is to get rid of these restrictions, right?
Okay.
And by the way, in OCaml, you also have this regularity restriction, right? When you have types like object types and polymorphic variants, OCaml will not accept types that are not regular, right? And it needs to reject them for decidability. Yeah. So how much time do I have? Because I think I'm almost out of time, right?
Well, you have. We expected that it should finish in 35 minutes, but it is not very strong restriction.
Yeah. Okay. So I guess I'll skip through this part because it's not that interesting. I see a question. Type x equals type fx. Okay, type checks, but should not. Oh, you tried it. Yeah, so I will come to this. Let's just have a brief overview of the MLscript type checker, and we won't get into this. So we won't get into the details. The type checking is done in several steps. The first step is to traverse the program tree and create type variables and emit constraints for the given program. Then we do constraint solving by decomposing constraints into simpler ones and recording bounds on the type variables. And finally, we do type simplification. And at the end, we do error reporting and pre-printing, right? So typing does the expected thing, right? So I'm going to skip over this. It introduces type variables for the parameters whose type it doesn't know, and then it uses subtyping relationships to register constraints. Then constraint solving is actually the interesting part, which is related to the question I just got in the chat. So the problem is that we want to know if a given set of constraints is satisfiable, or it does contain an error, and if it can be reduced. So the way we do that is that we decompose constraints between complicated types like function types into simpler constraints, and then we propagate the bounds that we infer on the type variables, so as to make sure that everything is consistent. All the bounds on type variables end up being consistent, otherwise we report an error. But this has problems, right? How do we solve constraints in general, right? And so the first idea I just described, which is to reduce complex constraints to simpler ones when it's evident how to do it, such as when constraining records, for example. And when you constrain type variables, it's also simple. You just register the bounds in the type variable and make sure it's consistent with the existing bounds on the other side of the type variable. But there are some problems. So, for example, what if you have an intersection on the left and a type on the right, which is not a type variable, so you cannot register a bound on it. So it's not sound to separate this constraint into two. It's sound to separate this constraint into two subconstraints, a less than t2 and t1 less than t2, but that's not necessary, meaning that you will lose principal typing if you do that. So we want to avoid losing information in a constraint like this. So what we do is that we use negation types. Thanks to the properties of Boolean algebras, we can actually rewrite this constraint into an equivalent constraint where the intersected T1 type on the left becomes a union not T1 type on the right. And you can actually show that this subtyping relationship, that this subtyping is equivalent to that subtyping. And moreover, this is not all we need. We also need some approximations, because otherwise we would have constraints that are ambiguous and that will require backtracking in order to solve. And so this is coming to the answer of the chat, the question we had in the chat, right? So if you have a record type, X with some type A and Y with some type B, and we have a constraint that is a subtype of this union of record types, then it's not clear how to proceed, right? We could make the constraint either about the left-hand side or the right-hand side, and it's not clear if we should constrain A to be less than T1 and B less than T2, or if we should make just B less than T3, right? And in general, there's no way to solve this without basically exploding the complexity of the algorithm by doing backtracking, which is basically impractical, or doing some approximation. And so that's what we do. And what we do is a conservative approximation in the meaning of the union type, basically. So in MLscript, a union type like this doesn't actually represent the set union of these values. It represents an approximation of this union, which includes more values and actually is equivalent to this type, right? So we basically forget about type X and remember only the types that are in the field X. We only remember the fields that are in common in all the record types in a union. And basically, we reduce this to a type that's more manageable for constraint solving. So we lose some information here, but this allows us to basically make progress and never backtrack in our constraint solving. It has some downsides, right? So yeah, thanks to these two ideas, we can solve all constraints of the complicated form where you have intersections on the left and unions on the right. And so the problem with this is that you cannot use the same encoding as in TypeScript, where you had a union of records with different tags that you could match on the tag. So this is something that does not work out of the box in MLscript. For MLscript, you need to discriminate the two parts of the union, right? So you can do that with class types, for example, because class types have nominal tags that you can use to distinguish values at runtime. So if you write a program such as this one, which tests whether a parameter X is an instance of C or D, and in each case accesses of a different field, then this will be given the type for A, something that's an instance of C and has a field U of type A, or something that's an instance of D and has a field b of type A returning A, right? And this is the principal type of this program. So if you remove the tags, then basically the two record types would collapse into an empty record type because of the approximation. So you need the class types to basically tag each independent record. Okay, and then we have some type simplification, which is actually quite involved and quite advanced, which allows.
Yeah. Like 2 times.
Sorry?
The previous slide, or the one before this, yeah, and that one. And yeah, the question is why this is the principal type.
Yeah.
It's like in most general form, this A and B, A kind of on the left of the OR and on the right of the OR could be different types, and we can return their, again, OR union.
Yeah. That's a very good question. Good point. So we could have an A here and a B here, where B would also be quantified, and return A or B. The thing is that in this configuration, A and B would not be distinguishable, basically, because they co-occur in positive position. And so basically you can show that this polymorphic type is equivalent to the polymorphic type that you described with A and B. To do that, you show that they subsume each other, right? So you fix the values of the variables on the right-hand side of the subtyping, and you make the ones on the left flexible, and you show that they subtype each other in both ways, right? In this sense, they subsume each other. So the MLscript type simplification algorithm is actually quite advanced, and it reasons about all these things. And in this case, it can tell that there's no need to have two different type variables. It unifies them and returns just a single type variables, which results in much simpler types. Because one of the difficulties with this approach is that you generate lots of variables, right? You really need to simplify as much as possible to reduce the amount of generated variables to make a type that's actually presentable to the user so that they can read it and it's not too complicated, right?
Right. And so, yeah, this for all is kind of how much does it bound? Still, we can pass the values of this with the fields having different types, right?
Yeah. So, for example, you can instantiate A to be int or string, right?
Yeah, makes sense too. Right. Yeah. Okay.
So yeah. Mm-hmm. Yeah, it's a bit counterintuitive, but that's a very important property of this system.
So I got a question about the pipeline. At what point do we perform like for all generalization?
Oh, so at every let binding, currently we do let based generalization. So let polymorphism, basically. Yeah, just like ML.
So you perform all the steps on the one let statement at a time. So first you generate variables, like do some like some steps, and then you generalize, and then you continue to do the same thing with the next let statement.
Yeah, and if you have so currently it's not implemented, but if you have a mutually recursive set of bindings, you would need to generalize them together, right? Like in OCaml. Does that make sense, or?
Yes, that makes perfect sense. Thank you.
Okay, cool. So let me go straight to the demo because that would be more interesting. So the demo that is actually online that you can try in the browser is not the most updated version of the MLscript compiler. We haven't actually updated it. So let me show you a more recent version. And I'm gonna share this screen. Oh, Oh, I need to join again. Okay, is it okay? In order to enable screen sharing. So I'll be back, right?
Yes, okay. You are muted. You are still muted. We can't hear you.
Oops. Yeah, thanks for letting me know. Okay, now it should be good. So here's a Scratch file where I can type expressions, and when I save, it basically tells us what the value is, right? So I can type things like functions and stuff like that, and it tells us that this has type int to int, and I can create classes. For example, let's say we have a literal class with a value of type int, and then I want to add a class for adding values together.
Also, so sorry to interrupt you, but can you like zoom in the editor?
Okay,
The
yeah.
text is barely visible.
Let's do that.
Control plus, I believe. Yeah, thank you.
Okay, and then you can do something, for example, like the left-hand side. Maybe you have a base class for expressions, and you say that literal is an expression, add is an expression with the left-hand side and the right-hand side, which are expressions. Okay, let's see what this gets. Okay, and then you can write functions such as eval, which will actually evaluate these expressions. So say if we have a literal, we just return x.val, and if we have an addition, we return x.lhs plus x.rhs, right? Oh yeah, I forgot the or. Okay, so
shouldn't we also eval left and right hand sides?
Yeah, I need to evolve this. Okay. Okay. Yeah, I need to make this a recursive function. Okay, and so we have an interesting type that's generated here. It's a recursive type, basically, that says you give me any a, and I return an int, where a is a subtype of either a literal or add, where the left-hand side is a and the right-hand side is a. And so this is because it keeps more precise types than the types we have specified, and it can be actually arbitrarily. You can encode arbitrarily precise regular types, right? In fact, for example, I could, instead of RHS, I could here put some other field name like test, and it would actually still work, and it would tell you I need an add instance that doesn't need an RHS field, so you may have removed it from the add instance, which is possible in MLscript, but it does have a test field which has this recursive type A that I need in order to process this this thing. Okay, so let's go back here, and an interesting thing you can do, just as a demonstration of the flexibility of the system, is that so this is closed recursion, right? Because when you evaluate this expression, you can only handle 2 cases, but maybe you want to add more cases later on, right? So what you can do is open recursion, where you can parameterize the eval method with eval itself, right? And every time you call yourself, you basically stutter eval of eval, okay? And this gives you a type that's also interesting. It's a type that still has an A, but it's no longer recursive. So it says, give me a function that, given an A and the left-hand side, returns an integer and an A. And that's actually the type of the eval function. So this is kind of a recursive looking type, because the and actually applies to this whole thing. And what it takes then as an input is either an add with left-hand side and left-hand side as a type variable, or a lit with val as the field value, right? And it returns either int or val, because int is the type of this branch and val is the type of this branch. And then you can actually close the recursive knot by calling eval, and that gives you a similar type to what you had before. But then you can add some cases, right? So you can define a new expression form, like maybe I can make this bigger. Let's say we want negation, so neg, which is an expr with let's say an underlying value, an underlying expr, and then you can define a new eval, call it eval n for neg, which will actually special case the evaluation for negations. So it will compute 0 minus the eval n of x dot underlying. Otherwise, it will actually reuse the eval function that we defined before, right? So you can define this function. It's fine. It gives you an interestingly specific type about this thing. And then again, you can tie the recursive knot such as this. Yes, so this one says this is not an integer, and this returns. Oh yeah, I forgot to pass the actual value here. Okay, and so this type checks, and then I can do eval n of, for example, add of right-hand side equals lit, val equals 1, and right-hand side equals neg of underlying equals lit, val equals 2. Okay, hope I didn't make a mistake. Maybe that should be a semicolon.
Should be eval n of eval n and then eval.
Thank you. Yeah, so that's what the error tells us here. It actually produces pretty detailed error reports. Okay, and so this works, right? It returns the value -1. Okay, so I think I'm not gonna. So do you want me to try anything else in the demo while we are at it, or any ideas, anything to break MLscript to embarrass me during the presentation? You can always try it online. So the online version is a bit older, as I said, or just compile the project locally and run SBT in order to try the tests. Okay, so if you have nothing specific to try, let's stop here, I guess, and let me conclude the presentation. Going back to the slides. Right, so there are many aspects of MLscript that I haven't mentioned, such as field extension. You can actually add any field you want to an existing value in MLscript. Computation types, which mirror the TypeScript notion of type computations. Overloading, type simplifications. Some of these are not yet completely implemented. So there are many things that go much further than what I've shown. Okay, and so the conclusion is that MLscript is supposed to be kind of like a TypeScript done right, with a better type system that's sound, that supports principal type inference, and that uses a Boolean algebra to express very specific types, which are still amenable to type inference. Right, and so that's it. These are the current contributors of MLscript, which are my students, some of my students. And yeah, if you want to join my research group, I would like to hear about it. And yeah, that's it. Thanks for listening. And any questions?
Yeah, thanks for the talk.
I have a question, sorry. Is it possible to make a truly nominal type to like set a barrier for the subtyping to not rip out of?
So what do you mean by truly nominal?
I mean, like an ADT in Haskell.
So basically, this system that I showed subsumes ADTs, ML ADTs, right? Any ML program using ADTs can be just implemented directly in MLscript using classes, and it will just work out, right? And it won't allow programs that use the wrong classes in the wrong places, even if they have the same shape, right? So in that sense, it is truly nominal, but it still has these structurally typed refinements to all values, right? You can take an existing class instance and say, refine it using intersections by saying, moreover, I want it to have a field of this type. You can even specify more specific types of its fields, right? And you can also make unions of arbitrary class types, even those that do not belong to a common ADT, right? So it's basically a generalization of ML ADTs, if you will.
Okay.
It does, yeah.
Okay, and another question: are the type variables rigid?
Yes. Yeah. So currently, as it's implemented, the ones you specify in annotations, in type annotations, are not rigid. It's like OCaml. But the ones that appear in class type parameters, they are rigid, of course, right? Because otherwise it wouldn't really be correct. So when you specify a class with type parameters, these type parameters are rigid.
Okay.
Also, yeah. Also, there's a subsumption checker in the implementation where you can provide a signature, a type signature, to make sure that the inferred type is a subtype of the signature you provide. And so in the signature, these type variables will be treated as rigid, right? An external type signature, basically.
The other way around, the signature should be a subtype of the inferred type.
In MLscript, the inferred type should be a subtype of the signature. Because...
Oh, yeah. I missed the notion of subtype again, sorry.
Right. Okay, yeah, good questions.
Yeah, another question. So you can generalize this Boolean algebra to anything, like, yeah, just distributed float is, it breaks at some point, right?
So there are many. So maybe by generalize you mean remove assumptions about the subtyping relationship. Yeah, so we need pretty much the full extent of Boolean algebras in order to message types during constraint solving, right? Especially this little trick of putting negations, turning constraints of this shape into constraints of that shape. This holds in a Boolean algebra. It wouldn't hold in many other systems. You need distributivity in order to properly reduce all constraints into basically unions of intersections, this kind of things, right? So I think you wouldn't be able to do much with pure subtyping relationships. I mean, the type system would probably still be sound, but type inference would not really work out, right?
Right, I see. On the other hand, if we're not doing like full inference, yeah, and I don't know, require annotations in some cases, we can do with weaker logic. Or
Which
weaker
logic?
algebra, I mean.
Oh, yeah. Yeah. So, for example, you could remove negations, right? It wouldn't break the type system, but it wouldn't allow us to give principal types to pattern matching functions that have default cases, and it wouldn't allow us to solve constraints with intersections in the wrong place.
Yeah, on the other, that negated types played a role with respect to soundness, at least in that example you showed.
Right, but you could always give a less precise type, right? You don't need a negation to type the thing. It's just that the type will need to be less specific. And so, for example, you could here say or I don't know, class 2, or just remove this part, right? And make sure that it's always a class 1. That's a sound type, but it's not a principal type, so it's not very satisfactory. There's no principal type for this function without negations, right?
Yeah, on the other hand, what if we remove top type?
You have a problem, I think. So the thing is that this is kind of like bounded polymorphism, right? This type system, it has bounds on type variables, even if they are not explicit. And the default bound on a type variable that's not bounded is top, right? So if you remove top, you don't really have default bounds, which will be okay, but it would be very painful to formalize. I think other things will break for sure. Probably in pattern matching. What would, you really want to reduce something like class 1 or not class 1 to top, right? Otherwise, other things would become weird.
Yeah. Well, I mean, in the same direction. Like if we remove negation and this type unknown, we still can have sound system. Yeah, it's kind of unobvious what will break or what will become tedious.
Yeah, but as you remove things, as I mentioned, you lose principal type inference, and type inference starts not working very well, but also it becomes not very user friendly. It becomes surprising for users, right? So users of intersections and union types, they expect commutativity, distributivity, associativity. They expect all of these things, right? So if you have some X an A or B, you can pass a B or A, right? Or things that distribute, etc.
Yeah.
So you
just don't remember immediately any like meaningful places where I saw this unknown type, and
right, it doesn't really come up that much.
Yeah, it seems kind of necessary in the presence of proper type variables.
So when you write a TypeScript definition, you know that TypeScript can have upper bounds, right? So type parameters can be specified to have an upper bound. Basically, the way you formalize this is that you say there's always an upper bound, and if it's not specified, it's basically any, right? Or unknown, right? The top. So that's where it occurs. It's not visible to the user, but it does occur everywhere, all over the place. Yeah, I guess you could try to remove it, but I think it's not really a good idea. If you want to prevent it from being inferred, so in languages like Scala, sometimes you get any inferred, and it's annoying because it means you have an error somewhere else. So you would like to get rid of this type, any, right? But in MLscript, it doesn't really happen, right? Because you never really infer any or unknown. You never really infer it because you always keep specific unions of stuff, right? And so the location of the error is always clear because also the provenances of all the components of a type are tracked specifically. So if you get the wrong union of things in some place, MLscript will actually pinpoint, okay, this thing flows into that place and it's wrong.
Yeah, right. Thanks.
Yep.
Another question is, do you use something like converting types into disjunctive normal form or something like that in the compiler?
Yeah, we use normal forms a lot for both constraint solving and simplification. So for constraint solving, it's important in order to reduce pattern matching constraints in a way that reduces the number of subtyping tests, basically. If you really need some form of normalization anyway in order to do constraint solving, because imagine you have a big ball of intersections and unions and negations, and you're given that, and we're asking it to be constrained to be a subtype of something. There's no way to make sense of this without normalizing this type in one way or the other, right? In order to get it back to shapes of constraints that you know how to deal with, basically. So you definitely need that in constraint solving. And it's also very important in simplification in order to remove duplicates from unions and to collapse, for example, intersections of two unrelated classes. We can collapse them to bottom, which can simplify some cases in the inferred types. So yeah, that's a very, very important technique that maybe I should have mentioned it in the slides because it's pretty important. Good point.
Another question: do you use a constructive version of like Boolean axioms or the classical ones? Because I heard that like in constructive math, double negation is not allowed and things like that.
Yeah. So this is classical Boolean algebra. We do have double negation elimination. Because this is really viewing types as sets of values, right? And you do complementation, intersection, and union on these sets of values. So you really want double negation elimination. Otherwise, a lot of things would break again, right? We could still add dependent types to MLscript and have a constructive logic based on this type system, which does have subtyping, which has double negation elimination. It would be fine, right? These are two different levels. It's not related to the way dependent type systems can be understood as intuitionistic logics, right? I don't know if that's clear. Or...
It's kind of clear, but okay, thank you.
Yeah.
I'm out of questions.
So Boolean algebras do necessitate double negation elimination, right? It's a basic. It's a thing you necessarily have when you have a Boolean algebra. Okay, thanks for the questions. Any other questions?
If not, we should probably wrap it up.
Yep. So thanks again for the invitation, and I invite you to have a look at the repository. So the language is not really in a practical shape yet. We're working on it. The parser will change. We'll make a new parser, and there's no documentation currently, so that's a problem. But yeah, let me know if you have any further questions, and if you'd like to collaborate on anything related to this. And yeah, I guess that's it. Okay, thank you.
Many thanks. It was great.
Yeah. Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.